Welcome to the videos for the first of two chapters we're covering this week, Chemical Kinetics. Let's get right into it. Kinetics is the area of chemistry that studies the rates of chemical reactions and the sequences of steps or mechanisms of how reactions occur. By reaction rate, we essentially mean the speed or progress of chemical reactions. This can be measured by the rate of increase in the amounts or concentrations of a product of a chemical reaction, or the rate of decrease in the amounts or concentrations of a reactant. Let's consider the reaction of the decomposition of dinitrogen pentoxide. The reaction stoichiometry is given by the balanced equation shown here, and the concentrations over time of N2O5 and the products, NO2 and O2, are shown in the table. If we graph the values in that table, we get this graph. As we would predict from the balanced reaction equation, the rate of formation of oxygen is 1/4 the rate of formation of nitrogen dioxide and 1/2 the rate of decomposition of the reactant N2O5. We can estimate the average rate of formation or decomposition at any given point by finding the slope between data points over a certain time interval. For instance, over the interval 300 to 400 seconds, we can plug in the values for concentration of N2O5 at those points, which gives us an average rate of decomposition of 1.9 times 10 to the minus fifth molar per second. The reaction stoichiometry relates the rates of formation and decomposition as shown here. We saw earlier that NO2 is formed at a rate 4 times that of oxygen, so the rates are equal if we multiply the NO2 formation rate by 1/4, or the inverse of its stoichiometric coefficient. We can relate the rate of decomposition of the reactant N2O5 similarly, but the rate is negative because reactants are consumed over time and so their concentration will decrease. For most reactions, the rate of reaction changes over time for reasons that we'll discuss later. It's especially important to differentiate between the initial rate, the rate at t equals 0 seconds, and the instantaneous rate, the rate at any given point along the graph. This can be found by calculating the slope of the line tangent to the graph at those points. The way that's determined depends on calculus, so I'll just show you the formulas later without getting into where they're derived. It turns out that variation in reaction rate has to do with the concentrations of the reactants themselves, which we can summarize in an equation called a rate law. The rate for any reaction will be given by a rate constant K, which depends on both the particular reaction as well as the temperature and other factors, multiplied by the concentration of each reactant raised to some exponent. Like the rate constant, the values of these exponents depend on the particular reaction and must be experimentally determined. Importantly, they can't be predetermined by just looking at the reaction stoichiometry. Some example rate laws for various reactions are shown here. Note that the rate sometimes only depends on the concentration of some of the reactants and not on others. And, if you look at the third reaction in the table, you can see that the reaction rate can be somewhat complex, depending on the concentration of 3 different reactants, some with different exponents. Let's see how we can use experimentally derived data to find the rate law for a reaction. What we need to do is run several experiments where we vary the initial concentrations of the reactants and observe the effect on the initial reaction rate. At first, all we know is that the rate law looks like the one beneath the balanced equation, with a rate constant K and the concentrations of the reactants, NO and O2, each raised to some unknown exponential power. We can use m and n for these unknown exponents now. We'll find the values in just a moment. Let's compare the results of the first 2 experiments. In experiment 2, the initial concentration of oxygen is the same as it is in experiment 1. However, the initial concentration of NO is twice as large in experiment 2 as it is in experiment 1. This is important because by varying only the concentration of one reactant, we know that any observed change in the initial reaction rate will only be due to the change in concentration of NO. What we see is that when the NO concentration doubles while the O2 concentration is held constant, the initial reaction rate quadruples. The question we need to answer is this. The ratio of the concentrations of NO is 2. What exponent applied to 2 results in a rate 4 times larger? The answer is 2 because 2 to the second power, or 2 squared, is 4. So the exponent in the rate law associated with the NO concentration is 2. Now how about the exponent that goes along with O2? If we compare experiments 1 and 3, we see that the NO concentration is the same, but the O2 concentration is twice as high in experiment 3 as it is in experiment 1. This doubling of the oxygen concentration produces an initial rate that is also twice as high. What exponent n applied to 2 gives us 2? The answer is n equals 1, since 2 to the first power is 2. So the exponent associated with the O2 concentration is 1. Like any variable in a math equation raised to the first power, we don't need to write the 1 explicitly. Let's recap what we just figured out. The rate depends on both the square of the NO concentration as well as the O2 concentration raised just to the first power. Reactions are often categorized by what's called their reaction order with respect to any of the reactants. The exponent of 2 means that the reaction is said to be second order with respect to NO concentration, and the exponent of 1 means that the reaction is first order with respect to O2 concentration. The overall order is given by the sum of these exponents. 2 plus 1 is 3, so this is a third order reaction overall. Now let's talk about the rate constant, K. First of all, not only does the value of K vary depending on the reaction, but so do its units. The units of K depend on the overall order for the reaction, and they are determined by the fact that each concentration is measured in molarity, and the rate itself for any reaction will be measured in units of molarity divided by time, typically seconds as the time units. For a third order reaction overall, this is units of 1 over molarity squared times seconds. Here are some examples of units for K depending on overall reaction order. Starting with zero order reactions, the units are molarity per second. Each time we increase the order by 1, we need to divide the units by molarity. So for a first order reaction, K has units of 1 over seconds. For second order, we divide by molarity again, and we get 1 over molarity times seconds, and so on. You might be wondering, what did you mean by zeroth order reactions? That's a reaction where the experimentally determined exponents for each reactant concentration are 0, which can happen in many circumstances. In this case, the rate law is just equal to the rate constant itself.